it would behoove me to spend just a minute to remind you that if you have a charged particle that is traveling in a circular path in a magnetic field, we know that it's QVB equals mv squared over r. And that from here, we could find the velocity. It doesn't matter what we find here. I just need to have a unified equation. So I'll cancel out the v's and we get QBR over m. Now, at the same time, the term period and frequency. Period is how long it takes to make one trip. That's 2 pi r divided by v. And frequency might be a newer word. You would have learned it last year, but in case that eludes you, frequency is the rate of oscillation. So it represents the oscillations per second. So it's not how long it takes to go in a circle, it's how many circles are made in a second. Does that make sense to see the difference? They're inverses of each other, so it's just v divided by 2 pi r. So they represent the same thing. We tend to use period for things that oscillate slowly, and we use frequency for things that oscillate quickly. So, that being said, I want frequency, which is going to produce QBR divided by 2 pi rm. And clearly the r cancels. We get QB over 2 pi m. Now, I hate to do this to you because I'm not trying to rub it in your face, but Q over m. I don't know that you've paid real close attention to this, but Q over m shows up all the time this year. Once a particle's moving, the charge to mass ratio seems to be all over the place. It is what Millikan discovered about the electron. He didn't measure the charge in the electron, he measured the charge to mass ratio. Somebody else measured the mass of the electron, thus we got the charge from there. So this charge to mass ratio can be measured tons of different ways because it shows up in so many different places. But remember, before we knew what electrons were, we didn't recognize that they were these small, tiny point particles. So this Q over m could have been any two numbers as long as the ratio worked out. So we had lots of ways of measuring Q over m, but not many ways of measuring m by itself or Q by itself. That comes later. What's important to understand here is that if, say, this is a proton, it doesn't matter whether I choose a proton or an electron. We know that the proton is streaming out an electric field in all directions. But now we're taking that proton and we're shaking it back and forth. I know it's going in a circle, but if you were to tip this sideways to you, do you recognize that it would actually just look like it's shaking back and forth? And this is by no means a particularly small number or anything. This is going to be a big number no matter what, because the mass of the proton, really, really small. 10 to the negative 31. Charge in a proton, 10 to the negative 27th. Charge in the proton, 10 to the negative 16th. So on its own, this value is 10 to the 11th, right? Without even putting any real numbers in there. Once you understand that, you recognize that this frequency is a pretty high number. Now, to put that in perspective, another way to measure light is by measuring the shaking of an electric field. In fact, that's what we thought light was before we understood the particle nature of light. What that means is a light wave appears to be an oscillating electric field. Well, shaking an electron in this way creates an oscillating electric field. This process will emit electromagnetic radiation, and it will stream away from the particles because it's shaking the electric field created by the particle. As I tried to explain yesterday morning, this creates the aurora borealis. So as charged particles come in from the sun and strike our magnetic field, they start to give off light due to their oscillatory properties, the fact that they hit a magnetic field and begin to cycle. Now, the magnetic field of the Earth is a little more complicated because it's three-dimensional and is not of uniform strength. So when we look at the magnetic field, especially near the poles, so if I make that the Earth, the magnetic field kind of comes out and back in, but it pinches together at the poles. So when particles come in, they tend to hit the outside edge, they get stuck, and they rotate inside there. So they start to spin faster and faster and faster and faster as they fall in towards the Earth. This is what causes them to glow, and also as they scrape against the atmosphere, they glow even more. So solar activity tends to generate and throw off lots of charged particles. When those charged particles begin to blanket the atmosphere, they begin to glow or cause the atmosphere to glow. We only see it in the northern and southern poles of the Earth because we need places where the magnetic field is coming back in from space and starting to scrape through the atmosphere, and places where the particles themselves have been collected in large enough groups for us to be able to see that as they spiral into the atmosphere. So these are all things that particles will do in a magnetic field. And I said, even as you were leaving, this is how you can generate microwaves. Your microwave oven generates microwaves by using a similar process of accelerating particles in a magneton that will spin them up and have them emit EM radiation in the microwave frequency. So we use the word microwave to say oven, but microwave actually corresponds to a specific electromagnetic frequency. It's approximately 2.4 gigahertz. Now, it should be a little bit, that frequency should conjure up some things for some of you who pay attention. I'm not sure if any of you pay attention. Anybody know what the 2.4 gigahertz range is? Yes, sir. Josh, did you have your hand up? Oh, okay. No glasses on, so I thought you did. What's that? Your Wi-Fi is at 2.4 gigahertz. Your cell phone is likely at 2.4 gigahertz. If you have a mobile phone in your house, like one of those ones that's connected to a landline, but you can walk around with it, it's 2.4 gigahertz. 2.4 gigahertz is largely a unrestricted area for people to make wireless transmissions, but it's a range. So when we say that microwaves are in this range, they kind of are. So it's one of the ranges that they use. They also use a one that's much lower too. It's funny because microwaves don't work the way you probably think they do. They are designed to grab the dipole moment of a water molecule. We know that the water molecule has a negative end and a positive end. And let's see if our chemist knows the answer to this. Because older microwaves just shook the water molecule, which takes too long to cook food. Newer microwaves break off one of the hydrogens because they force the water to turn so fast and releases energy into your food and then remakes the bond when it turns back around. Do you know the amount of energy in one OH bond in a water molecule? Yeah, neither do I. I just thought I'd ask our resident chemist. So, all right. So today we're going to change it up a bit. All this stuff about forces on free charges is nice, it's okay, but it's largely immaterial because the overwhelming, more productive thing is to look at the force on a current carrying wire. That's where we want to spend our time today because, to be honest with you, we don't have access to a lot of free charges. Just like when we were looking at this prospect earlier in the year when we did like point charges and their electric fields, those are kind of interesting, but not really that interesting. Mostly because we can't change anything about the particle except its direction. We can't extract energy this way easily. We already said from the beginning that we can't change the energy of the particles by the magnetic field. So that means we can't really interact with them in order to extract energy. On the other hand, a current-carrying wire affords us something that a free particle does not. A current-carrying wire is a wire that is filled with moving charged particles. For the time being, and just for this argument, let's assume that they are positive charges that are in the wire and that the current is traveling upwards through the wire. I'd draw a picture of this if I were you. In case you didn't know where the notes really began and the intro lecture left off. Now, a free charged particle that enters a region of space with a magnetic field will have its path bent. But current-carrying particles stuck in a wire are stuck in the wire, which means they'll be pushed to the side of the wire, but they can't leave the wire. So if there's a magnetic field in this region, like so, then the positive charges in the wire will all be pushed, and I'll give you a minute to be able to tell me whether it's left or right. I'm going to call out one of you, so you better break out your right hand rule. I said it in class. Oh, I wish you guys really actually listened to me. I'm not even sure why I talk. We stated by definition that current is the flow of positive charges in the wire, even though we know that's not what's happening. But if we start this conversation that positives are flowing upwards in the wire, then all of these charges are going to experience a force to the left. But they're constrained within the wire, which means that the entire wire is going to be pushed to the left. The wire will experience this force. This has several very important implications, and the first one being that they're not going to be caused to curve their path, because if the wire is straight, they must travel straight through the wire. Charges in a wire have to have a drift velocity that corresponds with the direction of flow of the charge, which is going to be in the wire. That means the entire wire experiences this force. The size of this force is I/L cross B. Current is not a vector, even though that doesn't make any sense to me. I don't like that it's not a vector. It bugs me that current's not a vector, but it can't be a vector because it's charge per time. It doesn't have direction. The wire's length, on the other hand, is a vector. So when we talk about the right-hand rule for current-carrying wires, the direction of the wire is your pointer finger, and your middle finger will still be the magnetic field, and your thumb will be the force. As you can imagine, this will also reduce to ILB sine phi, where that represents the angle between the current-carrying wire and the magnetic field. Now, a couple of pieces of station keeping here. First thing to be known is that length refers to the length of the wire exposed to the magnetic field, not the entire length of the wire, just how much of that wire is in the magnetic field. That is a critical piece of information. Don't discount it as Mr. Shelton just talking to fill up the dead air. These are the problems on the exam. Looking at the force on current-carrying wires. However, we really can't go on until we handle what I feel is the, I would say elephant in the room, but probably no one has posed the idea yet, that positive particles aren't actually moving in the wire. So this can't be what's happening. It should be brought up by somebody that it's a negative charge that is traveling in the opposite direction. Use either the left-hand rule or the right-hand rule to see what effect this has on our answer. To make it easier, you can always turn your paper around. You will find it to be easier than trying to point at your crotch. Andrew?
So when you're doing like the length vector, right?
Yeah.
How do you know which way the length?
Do you mean how do I know which way? Okay. Andrew's question actually makes perfect sense now that I think it through. The length goes in the direction of the current flow. Does everybody understand what I said? Really, these two things are combined. So I and L together tell you the direction. Does that make sense? All right. So what direction are the electrons pushed in the wire? To the left or to the right? So we understand that this is not an effective way of figuring out whether positive particles or negative particles are moving in the wire. Because you can't tell whether it's positives going up or negatives going down. So even now, we do not have a method for figuring out what's moving in the wire. Of all the things we've talked about all year, we have not yet been able to figure out a simple, straightforward way to figure out whether it's electrons moving in one direction or protons moving in the other. This is why it took so long. Our next topic, which we might get to today or might not, is called the Hall effect. And that's an explanation. It uses this. And it's a very ingenious lab, to be honest with you. I kind of like it. Well, we might do the Hall effect with aluminum foil to actually prove this. Either way, this is the force on a current-carrying wire in a magnetic field. It is based on the direction of positive current flow. So all of our discussion goes back to positive current flow. But you should be very aware of what's happening at the microscopic level, that it's actually the electrons going in the other direction. It comes up on the exam. And in your notes, you should make it clear that it doesn't affect the answer, that the force will still appear to be acting on positive particles moving in the direction of the current. Now here's the big deal. This force does work because the entire wire can now be moved inside the magnetic field. Unlike the other example where the particle's path was curved, although the force doesn't do work on the charged particles, the force can do work on the wire. And the best part about this is that this finally presents us with a method for making things move using electronics. Up to this point, there was no way to actually make something move. I know it sounds like we did, but if you'll notice, we talked about electric fields causing charges to move. But we never have a pile of electrons someplace. The closest we can get to a charged sample that we could push on with an electric field might be an ionized gas. Yeah, you can look at static cling and stuff like that as maybe being a force that moves some items, but never at will. You can put a switch on a wire and turn it on and off. You can have a permanent magnet, which means you turn it on, the object moves, you turn it off, the object stops. This is the creation of the first electric motors. And I gotta be honest with you, if you think back to all of the transformative technologies that humankind has ever developed, the switch-on electric motor probably ranks amongst the top 3. If you don't really appreciate why that's true, you should think of every single time you've activated something that moves using a switch. In a few minutes, I'm going to make a cup of coffee. I know the only reason I'm going to get that cup of coffee is there's a pump inside that pumps the water. That is a flip-on electric motor from the switch. Otherwise, I'd have to pour the hot water into a vat of grounds and then push the grounds out of the water. Because every single coffee pot that's made today uses a small electric motor. Old ones percolated. They took longer. New ones don't. The cars used to be started by hand cranking the motors over. You have a starter in your car, electric motor. Just your elevators, escalators. There's so many little things that use electric motors. And it's kind of unbelievable when you start really looking at it. There's a fan spinning in that projector. That projector couldn't exist without the fan in it. I mean, before the electric fan, people couldn't cool themselves in their homes. Right? There was no air movement, no air conditioning. Heating was radiators. Who's been up north or who's had a radiator in their house before? So you're the only person here who understands that you could be in a building that was built before electricity. Hot water was pumped up there by water pressure, not a pump. And you hoped you were low enough that the water would make it to your floor. It might not. Radiators usually use steam though, and then condensed it in your room and you hope it didn't blow. Nobody here who grew up in Florida has any idea about that. I would say that the only reason people live here is because of the invention of the electric motor. Could you live here without AC? You guys bitch when it's 80. So that being said, there's a whole lot of minor stuff I should bring up here. And we're going to start with some of the stuff that's in your homework, not because I think it's very interesting, but because we need a starting place. So you've probably looked a little bit at your homework. Yep, but I'm pretty confident that means some of you have not looked at it. How about, I know you have because you brought it up. Now, questions like this, where there's a resistor and a potential difference and a wire loop, they might give you the size of the magnetic field. These aren't particularly hard questions, but they do start the process of bringing up how big the force is based on other factors. And I think all of you probably recognize that when the switch is closed, the current in the loop can be determined by Ohm's law. I don't want to have to tell you things like that, but I think only about 3/4 of you would come to that conclusion. The other 3/4 would have to be led to it. So I'm throwing it in the face of the people who need to be led, i.e. didn't do as well on my semester exam as I would have liked. But once I close that switch, there's going to be a force on this loop. So tell me, what direction will this loop be pulled or pushed? So will this loop be pushed into the magnetic field or pulled out of the magnetic field? Having some trouble? When the switch is closed, is the current in this loop clockwise or counterclockwise? So the current will be this direction. Considering that's the opposite direction of what I just drew, that suggests the force will be to the right on this portion of the wire. But you should look at all of the portions that are in there, because all of the portions contribute. Unfortunately, the force here is down and the force here is up. So those two pieces of wire do not contribute to the motion of this loop. Wait. Eventually, the whole loop makes it into the magnetic field. Do you realize the moment the whole loop is in the magnetic field, it stops? That there's no force acting on it any longer. Because now I will have a force in this direction on that side, and this direction hasn't changed. So it will pull this loop into the magnetic field where the net force will simply become 0. Does that make sense so far? Yeah. All right. You know, if you reverse, so this is the railgun. Now, we're going to take that railgun and we're going to put it over a row of magnets so that there's a magnetic field that is upwards between the two rails. Right. Then we're going to connect a potential difference across the two rails. Now, if you've ever opened up a stapler and looked inside where the staples rest, I want you to imagine that that's our two rails. So these are like rectangular pieces of metal, something like that. Does that make sense? Just trying to kind of sketch it. So there'd be a rectangular piece there, something like that. So they're two rails. Does that make sense now? Because your projectile has to have a way of staying fixed to the track or to the rails. Now, the projectile doesn't have to be much, but it does have to be a conductor. So the projectile usually, in an example like this, is just a flat piece of metal that is able to slide across the rails. When I drop the piece of metal there, I complete the circuit, which means a current will be generated. In this direction. Now, I was careful to select the direction of the battery and the direction of the magnetic field so that you guys who won't do this don't have to verify that I've chosen it correctly for the right force, because some of you just sit there not doing the right-hand rule or scared like they're going to look silly doing the right-hand rule. But you should make sure I've done it correctly, because on your first quiz, I am likely to ask you to do this. We're all good? Yeah. But I want you to think for a moment, that's 3 questions, isn't it? What direction would the electric potential have to be for the rail to be fired to the right? What direction would the magnetic field have to be for the rail to be fired to the right? Or give you this and put a resistor in here, verify the current value necessary. You see all the different little things that go here, right? So let's go ahead and put that EMF and the R in here just so we have that. Assuming the rails and the bar itself are of low resistance, this will generate a current that is equal to the EMF divided by the resistance. If we also take into account that our rails are separated by a distance, say d, there will be a force on the bar in this direction. The thing that's pretty amazing about this is that the force on the bar is uniform. It's a single force that acts at its center of mass when we calculate it. But the truth is, it's a distributed force that acts everywhere along the bar. Now if you understand why I said that, you know why that's important. And I'm afraid some of you aren't really thinking like an engineer needs to, which is we need that rail to be accelerated uniformly across the rails, so that it doesn't come off the rail, right? If it was not accelerated uniformly, then it might have a path that's more like in this direction. Or worse, it might twist and get, kinked up inside the rails. Keeping your bar so that it actually acts as a projectile and travels across the rails, that's not easy. These are the kinds of problems that the Navy is attempting to accomplish with their version of a railgun. And they're not doing this. They're doing something a little different than this. So just so you know, there's to make a real railgun, you would not do it this way. For one thing, although this is a uniform force, and that force is equal to IdB. Please, right now, verify why I did that, because this is all over your exam. In some way, shape, or form, either this side or Faraday's Law, they're going to have you do a lot of this kind of stuff. We all good on that? Remember, it's IL cross B. L here is the separation between the rails. And then I probably should write this as EDB over R. We good there? E is not electric field. It's the electric potential. It's the EMF. So now we have the force in terms of given quantities. You guys following that? That's the kind of stuff you have to do. But if the bar has mass, then this has to equal MA. This will accelerate the bar to the right. So the bars are L long. We should be able to figure out how much kinetic energy the bar has due to its acceleration across these bars, across these rails. That's a railgun. Now, let's just go one step further with this so that we begin to get an appreciation of it, okay? If you're really, really able to connect mechanics with this, you understand that the work done by this magnetic field would have to equal the change in kinetic energy of the bar. You guys following where I'm going with this? So, I can't do what I want to do. That's pretty low there, but I'm going to go one step further on this screen, and that's simply to say that that's the EMF times D times B over R times L equals 1/2 mv squared. We good? Now, to make this a projectile, to really make it work the way you'd like, you solve for V and you figure out what you have to maximize to increase the velocity. And you're going to notice right away, even without doing any solution here, that everything in the numerator is what needs to be maximized, correct? But that's not as obvious, that's not as easy as it sounds. First, you really don't want to maximize D. You don't want to make it very wide. So that means maximizing B and a potential difference. It also means making it very long. Unlike a standard gun where the energy comes from the chemical reaction in the gunpowder or in your other form of propellant, this one continually accelerates the projectile along the rails. So the longer the rails, the more velocity you're going to get. In a rifle, that's not true. In a rifle, the length of the rifle helps allow you to collate the bullet better and use more of the energy of the expanding gas. The longer the barrel is, the more that gas accelerates your bullet and doesn't escape into the atmosphere. It also allows you to spin the bullet, which, although we haven't gotten to angular momentum yet in mechanics, you should remember it from last year. If you can spin that bullet, it's going to tend to want to stay in the same orientation and not tumble. That means it'll travel farther, right? You can design your bullet then to be aerodynamic. The problem with this is it's hard to design this to be aerodynamic. Can't you see why? It's got to be wide and go across those rails. So you're starting to see some of the limits here. So the Navy is experimenting with this, but they would never do it this way. And part of the reason is friction. And we're going to lose a lot of energy due to friction, not to mention that I want you to imagine how I would make this if this were me. I would have thousands of those bars stacked up dropping them on the rails, because every single bar will receive the exact same acceleration, will be fired off the edge of that gun. This will rapid fire them with no propellant. Remember, these are inert pieces of metal being dropped on the rails. So you can fire them as fast as you can get them on the rails. There's no cartridge to be thrown out. So most of your guns, if you guys have looked into this idea of having a machine gun, has a long strip of individual metal cartridges that have your propellant and your bullet in them. Each cartridge has to go into the chamber, be ignited, fired, and then ejected before the next one can come in the chamber. This is why they jam all the time. That's why they're always cleaning their gun to make sure that everything works flawlessly. And although we're really good at it, when you have M16 is a very effective weapon. The truth is, every single time you're going to eventually run into a jam or a misfire or something like that. This won't misfire. As long as the metal hits the rails, it's going to shoot it off. But there's friction here. A real weapon like this will melt inside a couple of minutes because all that friction on the rails is eventually going to melt the rails. It's going to get really hot really fast. The Navy's version of this is to try and generate the current without having to touch the rails. They want to induce a current so that they can levitate the bullet and then have the bullet be accelerated in the same way that a maglev train accelerates. That way there's no friction. Maybe a little air resistance, but that can be mitigated. So that requires something a little bit more elaborate. So what the Navy's working on isn't this. This is something you could build in the classroom and you can see staples go across your desk. It's not particularly exciting. But, you know, it's a railgun. It's the basics of a railgun. And it represents the basics of a lot of simple questions in physics. And you can imagine all the little things we can bring together here, right? I mean, one thing that I have not talked about yet is you should, as smart students here, recognize that the power dissipated in the circuit looks like that, correct? Well, the work done by the electrical circuit can be based on taking that power and multiplying by how long it takes the rail to go across, the projectile to go across the rails. If you can figure out that time, you can figure out the amount of electrical energy expended. So as a follow-up question, because you guys know kinematics, and I'm not going to do this, but you should show that the final amount of energy will be equal to the electrical dissipation. That without friction, there's no loss of energy. That 100% of the electrical energy will be converted into mechanical work. That's the other reason these are kind of nice. You don't get that from most propellants. But the electricity requirements are extreme. So usually you need a huge, huge amount of electrical power, thus Navy. Their vessels have nuclear reactors. They have an unlimited source of electricity. Remember, you can plug a carrier into a city and power a city. They do it. They do it all the time, actually. Whenever there's some kind of major catastrophe, we pull up with one of our carriers and we plug it into the city and power their city from our aircraft carrier. Remember, it's a 30-year nuclear reactor. And most of our nuclear reactors that are running on something like an aircraft carrier, you've already got like 10, 20,000 people. I don't know how many people are on an aircraft carrier anymore. I used to know. But it's a lot of people living there. But they power cities when necessary. It's pretty phenomenal. So, the railgun. Chase, you had a question?
I was gonna say,
The magnetic field allows us to do something we could not do before, and that's something I really want to talk about too for a quick brief moment, and that is we can figure out what the charge carrying particle is using the magnetic field. Now, yesterday when I showed this example, I was able to show you couldn't do it, right? It didn't seem to matter what direction the current, whether it was positives going up in the wire or negatives coming down in the wire, the force on the wire was the same. So, believe it or not, it was a very quick trip from that to what's called the Hall effect. Hall as in I'm spelling it right now so you don't have to worry about it. The Hall effect. Because if you were really paying attention yesterday, you could have seen where this was going pretty easily. So consider for a moment the Hall effect, and that is, it's an interesting idea. It's a circuit. And to make the circuit, we're going to need an area space that has a magnetic field, because obviously the Hall effect, like anything else that we've been talking about, is going to exploit the magnetic field and this force on charged particles. Now, yesterday when we talked about this magnetic deflection, we recognized that the magnetic deflection actually occurred at the atomic level. It was happening to the individual charges, but the charges were confined to move in the wire. So what if, instead of using a wire, I took my wire and flattened it out? Imagine, instead of a wire, a strip of aluminum foil. So this now, let me actually draw something different than that. Let me draw it as a square with a opacity in the middle. Let's see, will that work? Yeah, that's good. So a strip of like aluminum foil. So it is a conducting foil that is placed inside the magnetic field. And I use a adjustable resistor and some EMF. Now the Hall effect is interesting. It capitalizes on what we know about the motion of charged particles. If current is the flow of positively charged particles, then a positive particle, can you even see that dot, that blue dot? No? How about, I don't know, trying to find something nice and dark. Can you see that dot? All right. If this is a positive particle and it travels into this area with a velocity v, what direction will it be pushed by the magnetic field? Just turn your paper. So towards me or away from me? Yeah, towards me, right? So this particle will be deflected this way. Okay? Now what that means is that as the electrons pass into the foil, they're going to drift to the right side of the foil and begin to set up on the right side of the foil. And they will be pressed to the side until the magnetic force on them to the right is balanced by the electric force. Look, as they start to line up on the right side of the foil is going to become positively charged, which is going to create an electric field that's going to be in this direction. They'll do that until the magnetic force and the electric force equalizes. So eventually, I'll get this stable group of charges pressed to the right, suggesting that there will be a potential difference between both sides of my strip. Right? Now this only works, this works, period. You're going to get this happen. But it has to be clear that the potential difference is going to be positive in this direction. Right? Towards where the positive charges are. That'll be my positive potential difference. So if I put a voltmeter on the strip, I should see a positive change in potential. If I measure the width of this strip, I should be able to make a prediction about the size of the electric field. These three sentences are things you should write down, because where I'm going with this is going to have value, and I'm going to rely on you to do this. Because the electric field here can be, again, related to QE equals QVB. And V here is the drift velocity. Do you remember we calculated the drift velocity a couple of months ago? So not only should we be able to figure out what's being pushed to the side, but the drift velocity, if you look back at your notes, and I'm not asking you to, was related to the physical amount of charge per charge carrier. The Hall effect actually allows us to measure quite a bit. And I want you to look into your expression for the drift velocity from a couple months ago to see this. Because the charge cancels out here, but it doesn't cancel out in the drift velocity equation. So in this particular lab, we can figure out the charge on that particle. But it's not enough for us to figure that out. Our goal here is to figure out what's happening to our particles. Is it positive charges moving or negative charges moving? So let's consider now what would happen if instead these were negative charges moving this way in the wire. What would be the direction of the force on those? Also to the right. You see that? They're also going to be pushed this way, which means if they're negative particles, I'm going to get a bunch of negatives lining up over here. The obvious result here is if you set up your voltmeter across your strip and know the direction of the current, if it's a positive potential, then you know it was positive charges. But if negatives line up over there, the electric field will be in the opposite direction. And therefore, the potential will be positive to the left. This simple experiment can tell you whether it's negative charges or positive charges that are drifting to the side to push on the wire by creating a potential difference inside the wire. So the potential difference is measured across the strip. So we're just going to take strips of aluminum foil, place them right down on our strip of magnets, run our deflection lab first, and then our Hall effect lab right after. Because we're just going to pull the wire off, put the strip down, tape the strip there so it doesn't get pushed around, and then measure the potential across the strip. Seem pretty easy? Should be pretty cool. I haven't done it like this before. I'm looking forward to seeing if it works. Questions to this point? All right.